I think it's preparing.
Yes, yeah, it's working.
Okay, so thank you for coming. And I am Francesco Clerici, and I'm going to present the role of ENGYS in this quantum CFD project. This is the outline of the presentation. I will present the ENGYS company and the team involved in this project. And in the second step, I will present our participation in the project. And then I will show the activities that we've done to date and a short 6-month plan. So ENGYS is a global provider of CFD products and services. It has been founded in the UK in 2009. And basically, the main idea is the open source CFD code for the enterprise. And we have two main products. The first one is Helix, which is based on OpenFOAM. And the second one is Element, and it is used for automotive. And we have 50 personnel staff in 8 different countries. So this is the team involved in the Quantum CFD project. We have Eugene, who is here today, and he is the CEO of ENGYS UK. Then we have Paolo, who is the administrator of ENGYS Italy. Then there is Pavlos, who works mainly on the core adjoint team. Then we have Leonardo, who is here as well. And he is working, he's a QCFD researcher, and he's working in parallel also on algorithm, on CFD algorithm. And then that's me. I am a junior QCFD developer, and I work also on the adjoint CHD, conjugated transfer development.
Paolo, sorry to interrupt. We see the presenter screen, not the projector screen. I don't know if you could swap it on the Zoom.
Yeah.
There's a few boxes there blocking the slides, actually.
Oh, yes.
Okay.
No.
So far, it hasn't changed yet. Now it's changed.
Yes,
changed.
perfect.
It's changed.
Okay, it's working.
Cheers.
Okay, so concerning the QCFD participation, we are involved in 6 different work packages. The first one, in which we are putting, let's say, the 6% of the effort, involves the creation of simple CFD examples and benchmark. The second work package, in which involves us at the 23%, involves the say the creation of industrially relevant benchmarks and example, like the conjugate heat transfer optimization problem. Work package 3 is, let's say, the core work package of the project and concerns the conversion from classical CFD optimization problems to quantum CFD, and in particular is aimed to solve the problem, the benchmarks of the work package 1 and 2. Then, if I can change slide.
Now if we click, yeah.
Okay, yeah, perfect. And so the fourth work package is the 8th one, and concerns validation, benchmarking analysis. In particular, we are going to study and develop two to basically to compare the classical CFD methodology and the QCFD in terms of errors, so how much the solution to obtain the solutions differs, in terms of algorithmic complexity and in terms of execution times. Then the work package 9 is, let's say, the most relevant one for ENGYS because it concerns the open source integration and dissemination. So what we're going to do here is to create an interface for the QCFD backend, which is based on open form, like, for example, by using dictionaries and similar configuration files. And finally, we have the work package 10, which concerns the project and data management and the communication of the results of the project. So now I just make a brief in-depth of the work package 1, 2, 8, and 9. So concerning the work package 1 and 2, we are mainly involved in the, let's say, creation of the CHT adjoint benchmark. CHT stands for conjugate transfer. And this is aimed for battery cooling optimization in electric vehicle. And what we want to do is to find an optimal topology of the serpentines, which are basically cooling the battery. And such problem has three main steps. The first one is the resolution of the primal problem. So to solve Navier-Stokes and possibly a turbulence model equation inside the serpentines, to model the thermal behavior of the battery. Then the resolution of the adjoint problem of the first primal problems. And finally, the overall methodology consists into optimizing the topology of such serpentines. And of course, there is also a geometry modification part. And the two main challenges in this benchmark concern first the fluid-solid couple adjoint formulation. So the adjoint of the thermal equation of the fluid and of the solid should be solved at the same time. And the second one is the geometry description, because basically we have to satisfy some construction constraints. Then this is let's say a draft on how the classical, how the interface between the quantum backend and the classical, let's say, CFD should be structured. So we start with the mesh, the boundary condition, the transport properties, and numerical schemes, which represents the classical input. So these are, let's say, these are the data that a classical user should provide to the interface. Then there is the first layer, which represents the logics, which concerns the conversion from classical algorithm to quantum algorithm, and it could be based on variational quantum algorithm, matrix product state, tensor network, etc. Then the second step is the creation of the quantum circuit, solving such quantum algorithm, and concerns the implementation. And then we go back to the classical interface by providing a classical solution, which can be used for post-process. So, concerning the progress we've made up to date, basically we studied a lot, fundamentally how to represent linear operators into quantum gates. Especially, we studied the one-dimensional Laplacian. We studied the centered finite difference one-dimensional Laplacian and its gate level implementation. For example, here there is an example of a 5-qubit circuit which applies the discrete Laplacian to a transverse state. The transverse state represents the ground state of the kinetic energy inside the Schrödinger equation. And in parallel to this, we also worked on the implementation of the adjoint on the CHT fluid solid thermal couple adjoint. Next, this is just a brief overview of the perspectives. So what we want to do is to use MPO, so the matrix products operator, to create quantum networks, and to for implementing specific cost function, which are important for CFD computation, specifically for optimization problem like the CHD. And next, there is of course the implementation in terms of quantum circuits. And finally, another aim is to provide classical simulations, always referring, for example, to the CHD adjoint in order to compare the solution obtained with the classical CFD and the quantum CFD. And of course, the final aim, which is the say central objective of ENGYS, is to provide interfaces for classical end users. So concerning the plan for the next 6 months, we plan to work on the adjoint of the Schrödinger-Laplace-Poisson equation. So let's say equations that are involving one-dimensional Laplacian, and to work also on the primal and on the adjoint of the CHD problem. Then we are planning to implement actually such algorithm in QSkit by using the variational approach. Then we could try to step to 2D or even 3D, and to make, let's say, algorithms which are independent of the number of qubits. And then we are planning to start to provide some interfaces for OpenFOAM, which are more based on OpenFOAM dictionaries. While concerning the work package 8 and 10, we are not taking any action. And this concludes the presentation.
Right, thank you very much. Are there questions, please? I do have one question. What are these OpenFOAM dictionaries? So how do they work?
So OpenFOAM dictionaries are like configuration files in which you declare, let's say, you basically declare everything. You can declare the mesh. So for example, the bounding box of the mesh, how many discretization volumes inside of it. So you declare the numerical schemes, like, I don't know, the Roy solver, the HLLC solver, and also like the physical properties, like also boundary condition. You would basically declare everything.
Is that a standardized dictionary? I mean, is this something that is universal, or is it?
No, they are typical of OpenFOAM. Yeah.
Okay.
But they are quite.
It's like XML, right?
It's like XML.
It's like a markup language, but it's specific to person.
Okay, but it's also structured like XML, or
it's not declarative like XML. It's implicit, so it's a little bit archaic in that context. But this thing comes from the early 90s, so happens from Slack.
oh, okay. So I see. So it basically works like a batch script or something like this.
No, not at all.
No?
It's just a container. It's a standard filterization for information. So keyword value.
Ah, okay.
Stuff like
Right.
that. So,
And the keywords are defined, and there is some list. Okay, I see. And so basically, that's what users would give to OpenFOAM, and then OpenFOAM goes away and solves the problems with that.
And it's like in XML, you can either use whatever front-end GUI type of thing, or most of us are more familiar with directly typing it in.
Right. Yeah.
That's just the technicality. I think. The more difficult, what we discussed earlier, is how to convert geometry into whatever MPS.
So is that the standard that is being used? These scripts, or is this used by most users or not? I mean,
I think we need to go through the process in some detail. I mean, maybe we can at the next meeting or sometime online we can give a training course just in what is the process, and we can get because I mean we probably missed something, so it'll be so ingrained.
Yeah. Okay. So basically, that would be useful to know basically what is the step by step. If somebody wants to use this, how do you go step by step, and then submit it? So that would be useful for us to understand. I think that would be great.
Yeah, but I think it's very different from what we can aim for at the end. At least in its
Right.
So the concepts that are important. Obviously, we talked about just resolving everything, and everything about CFD. A very large part about the classical CFD is about how not to resolve everything. Right, how to be efficient in terms of your application space on this innovation. So that's a really key.
Are there any other questions?
Yeah, just a quick question. That 5-qubit Laplacian circuit, is it implemented or?
This one?
Yeah. Is it implemented in some sort of,
Yes, it's implemented in QCFD.
is it so? Wonder if you can run it on the real quantum signal?
Yeah.
Um,
Yeah, but this applies Laplacian to a quantum state.
yeah,
It doesn't solve the Laplace equation, of course. Yeah.
And what have you done with this? I mean, have you used that for?
No, we just tested
tried
it.
it.
Yes, because we are still at very early stage. So yeah.
We don't need to do, everybody doesn't need to, we just need to provide an interface.
Yeah, absolutely. No, I
We need to